Okay, so our last lecture we proved the we talked about automorphism, and we looked at the inner automorphism determined by some element A. And what we'll do now is we'll talk a little bit more about automorphisms. Every group has at least one automorphism, namely the identity map. What about others? Well, if G is an abelian group, then the mapping that sends X to X inverse is an automorphism. So abelian groups always have more than one automorphism. The key is, why is that? Well, if we look at GH inverse, that's H inverse, G inverse. But if it's an abelian group, that's the same as G inverse, H inverse, which is, if you want to think of your function f of GH, f of G times f of H. So it's certainly a homomorphism. Y is it onto? Take any G in the group G, then f of G inverse is G inverse inverse, which is just G. So the map is onto, since given any G in the range, we can find that G inverse is part of the group, and in the domain that will map to that G. And then finally, if f of x equals f of G equals f of H, that means G inverse is equal to H inverse. So G equals H, because inverse is a unique in a group. So that's an automorphism for an abelian group. Let's look at something that's not an automorphism. Let's define alpha from Z cross Z2 to Z2 cross Z2. Well, the identity is the identity. F of 1, 0 is 1, 0. F of 0, 1 is 1, 1. And finally, f of 1, 1 is 1, 1. So you can tell by that definition it's got to be onto, right? I think we've hit all four of the elements. It's 1 to 1. We can see every element gets mapped to a different element. You know, note two of the values of alpha on an element are the same. But I don't think it preserves the operation. I think I look at alpha of 1, 0 plus 1, 1. So if we add that, again, this is mod 2, so that would be 0, 1. And that would get mapped to 1, 0. While alpha of 1, 0 plus alpha of 1, 1. 1, 1 gets mapped to 1, 1. 1, 0 is mapped to 0, 1 plus 1, 1. And that would equal let's see, 1, 0. But that one actually would be an automorphism, at least on this one, right? This would also be 1, 2, which is 1, 0. So maybe they do agree. Let's check a different one. That's not enough to show it's an automorphism, right? That's just a homomorphism even. That just shows it agrees on these two elements. Let's try two different ones. Suppose we looked at 1, 0 plus alpha of 0, 1. So 1, 0 would be 0, 1 plus 1, 0, which would be 1, 1. But it's still going to agree on the sum. Let's see. Right, because the sum, these two added together will give us 1, 1, and alpha of 1, 1 is defined to be 1, 1. So again, that also proves it's preserves the operation for those two elements. I think it should be the same. So this actually, I think, should be an automorphism. At least we haven't still proved it yet. We have to check because obviously there's two. It's abelian, so there's two choices. There's 4 elements. There's 4 choices for what goes here. There's 2 choices for 4 choices. Each of those have 4 choices for what goes here. So there's 16 different ones. So I don't even think this mapping would be an automorphism. But anyway, we'll maybe come back to this. At this point, we haven't. Those calculations do not disprove that it is an automorphism. So we'll just leave it at that and move on. Again, I'm trying to look at the pairs. I've got a 1, 1 and a 1. I think this one very well may be an automorphism. Did I check 1, 1 plus 0, 1? I just did here. That's 0, 1 plus 1, 0 is 1, 1. And if I add them together, it's 1, 1. So that would be an automorphism, or at least we can not disprove it.